In this video, we're going to talk about electric power. For example, suppose this battery is connected to a device. An example, this device can be electric motor, electric heater, stove, pure resistor, a storage battery, a toaster, anything. The battery will step up electric current I. This is a fuse to step off electric current in this circuit. Now at this point A, it will have a higher potential than this point B. This is because the power or the charge that is being generated is coming from this positive terminal. And since it's coming from this positive terminal, it moves in this direction. Remember, electrons move from negative. The charge moves from positive. So since power is defined as the rate at which work is being done, therefore we can say that P is equal to du, that's work done or energy, over dt, change in time. Change in energy or work done over change in time. And it is equal to IV. So if the device between this A and B, this device, if it is a pure resistance, the energy will appear as heat in the resistor. Okay, and we can use Ohm's law and rewrite this equation and say that P equal to IV is equal to, we can write I. Instead of V, remember, according to Ohm's law, V is equal to IR. So we can say times IR. So if we resolve this, we can have that P power is equal to I times I is I squared, then R. We can also say it is equal to V squared over R. So these are the units of power is watt, or you say joule per second, joule per second. So you can say joule per second, or you call it watt. So let's look at an example. An X-ray tube takes a current of 7.0 milliampere and operates at a potential difference of 80 kilovolts. What power is dissipated? Now, simple. We can just say power is equal to IV. Now, I is current. This is the potential difference. Now, what that means is that I, they gave to us is 7.0 milliampere. So we can convert it to ampere by saying 7 times 10 raised to power minus 3 ampere is now in ampere times V. V is 80 kilovolts. Kilo is 1000. So we say 80 times 10 raised to power 3 volts. If we multiply that out, we're going to have 560 watts, or you say joule per second. Another example we can look at is this. The wiring of a house must be thick enough so it does not become so hot as to start a fire. What diameter must a copper wire be if it is to carry maximum current of 40 ampere and produce no more than 1.8 watts of heat per meter of length? Now, we have that power is equal to IV, and we also have that it is equal to I squared R. We've already seen that. This is what we can use to solve because it shows us that R is involved. Now, since R is involved, remember previously we said that R is equal to rule L over A. So with this, we can say that area can be rewritten and say that R is equal to rule L over, instead of area, we can rewrite area as pi into d diameter over square, since this was given to us in terms of diameter. So diameter over 2 into squared. And having seen that p power is equal to I squared rho 4L over pi d squared, if we resolve that. So using this formula, we can fix in the values, or we can even alternate to make it easier and bring in I squared to come and multiply L. So from here, we are asked for the diameter. So if we make diameter subject of the formula from here, diameter is what we are required. So we have that d is equal to square root of, you can say, 4L rho, or let me put I first since I comes before L, 4I squared rule L over over pi p over pi p. So this will be the formula. So if we fix in the values, you have that d is equal to 4 times 40. Our I squared is 40, so 40 squared times our rho is 1.6, because that's the resistivity of copper wire is a constant, is 1.67 times 10 raised to power minus 8. Then the length 1 meter over pi is a constant as well, 3.142. So if you multiply it with the power given to us is 1.8 watts. So if we calculate with calculator everything, we're going to have 4.4 times 10 raised to power minus 3. Remember, square root meter. So this is the diameter.